Okay, we're down to only one assignment posted there, I see, so I'll have to work on that. We're starting a new section today, though. We just have one more example to finish, this Newton's Law of Cooling example to finish from differential equations, so we'll finish that quickly, and then we're going to talk about more about applications of integration, not new integration techniques, but applications, and this one is an extension of the basic application of integration that you learned in Calculus 1, which was computing area under a curve. So we're going to extend that a little bit to computing volumes of solids today, okay? But we have to step back a little bit in order to understand this application of integration. We have to step back and remember a little bit, review a little bit what definite integration really means, because it's easy to lose sight of when you're doing a definite integral, which is what you use to compute area under curve, right? Definite integral means you have limits of integration, correct, right? But when you're doing a definite integral, it's because of the fundamental theorem of calculus, that is fairly easy to compute, all right? But so you kind of lose sight of what definite integration really means. So we need to step back and recall what it is we're really doing when we're carrying out the process of definite integration, because we need to understand that to understand how we're going to compute volumes of solids as opposed to areas of regions. Okay. All right. So that's what we're taking up today. But before we do that, I want to return the test to you. Right. Okay. So I'm going to pass these out. So some of you need a second opportunity here to demonstrate your knowledge of the fundamentals here of the things that we learned in test number 1. So as I mentioned, I emailed you guys right about the test grades being posted. So we will have a makeup opportunity following the lecture on Wednesday. It's Wednesday, and so the last 45 minutes of class or so, we will have a makeup opportunity. Okay, it won't cover the entire test, but only some key problems from the test. So those are posted there. These problems. So when you're reviewing test number 1, if you're preparing for that makeup, you want to focus your attention on these problems in particular, right? Okay, to prepare for that makeup. All right. So now, don't come in and just don't prepare, don't have this strategy of, well, I'm not going to prepare for the makeup, but I'll just come and see how I do on the makeup. That's not going to work, okay? So, because if you don't get 70% on the makeup, then you're not going to get any points at all, right? Okay, so it's not a matter of just, I'll do 1 or 2 that I know, and then I'll get some points from that. You won't get any points that way, okay? So you've got to review everything and try to do well on the makeup, okay? So this is why I'm... Oops, did I give the right person to the right test? No, I don't know what I'm doing. All right, so Ben York. I'm hoping to learn some names here when I pass these out. So Mona sits right there. Mona, I know. Pedro sits right there. So do prepare for the makeup, right? Okay. That's your first step to sort of rehabilitating your grade if you need that. Edwin? Yes. Now, some people scored really well on the test, so if your grade is a high grade in the 90s, then probably the makeup is not going to benefit you too much, all right? So you may not want to be thinking about the makeup so much, because there's no way, even with the makeup points, to score above 100, all right? The points you get from the makeup will be the makeup points you get will be determined by what your original test grade was, and of course how many points you earned on the makeup test, right? And so if your test grade was high, then that means you're not going to have a lot of points added to your score. But if your test was low and you do well on the makeup, then you can have maybe a lot of points added to your score, right? Jesus, is Jesus here? All right. Alejandro? Janaya? Elizabeth? I know. Okay. Beatrice? Raja? Armando, I don't see Armando. I know Armando. Zhao, here. Ashley? Ashley is, oh, Ashley. Okay, Ashley. Aaron. Is it Aaron? Louis Martinez. Me? Is it me or my? When? When is the last name? Is she signaling me? Not here. Christopher is here. Yeah, this is Mr. Wynn, but I'm glad I know that now. Michael Figueroa. Nick. Emily. Stephen Flores. Nicholas. Samantha. Nicholas. Samantha. Joseph. Is it Jasnari? Is that how you say it? Gonzalez? Is that person here? That's Mona. Matthew, did Matthew here? I know Matthew. Anthony, where's Anthony today? Aliu Martinez. Mr. Martinez, or Chris, the other Christopher Mona. All right. Okay, so now, again, if you came in late, be aware of this message, right? Okay, so about the makeup opportunity and that you want to focus on these problems. So Taylor will review these problems, all right, during her session. So on Wednesday, you'll have your opportunity to review with Taylor on those problems, right, before you come to class and take that makeup. But in the meantime, you can also go to the Math Center, right? Okay, and ask them. They'll be happy to help you, as you know, if you have your test, right, and you want to know about particular problems. Of course, the answer key is posted, or you can come to my office, right? Okay, so you can find me, and I'll be happy to explain how problems were done. All right, a lot of that you can tell from the answer key because the answer key has the complete solution written out. All right, but if you're not following the solution that's on the answers, then you can, again, go and ask, right, for help. All right, now, look, for some of you, right, the first step, as I mentioned, right, toward pulling your grade up, if that's what you need to do, is focusing on that makeup, right? So you need to use that as a practice run for the things that you're going to need to do for the rest of the semester to keep your grade up. So that would be going to tutoring either with Taylor or in the Academic Support Center and preparing, right? Preparing for tests, right? Okay, starting with preparing for this makeup. So some of you were not properly prepared for the test, okay? So you did not do the review as I told you repeatedly that you needed to do, but some of you did not do that. And you're not prepared for the test. So you cannot make that mistake on the makeup and on tests going forward, right? Okay, you're going to have to prepare as best you can. Now, another issue with the test that I also warned you about, but it came up repeatedly. So on some of your exams, I had to scold you about this, all right? But next time I'm going to be meaner about it, all right? You cannot give me a calculator-derived answer, right? Okay? So many of you wrote nothing correct in terms of steps to solve the problem. What you wrote down there was nonsense, but then you suddenly wrote the correct answer. So that is that is called cheating, folks. That is what that is called. So you cannot do that. You just cannot do that. So now you may slip that by me, once or twice in the semester, but it'll be an insignificant number of times. I'm going to spot that, okay? And then I'm going to give you no credit for that, all right? And then it will irritate me. So if it irritates me enough, then I'm going to start penalizing you in other ways other than just taking the points off, okay? So so you just have to not do that. So I hesitate to suggest this, but for some of you, I think you need this. You're going to have to put it when you're doing your homework or doing test reviews. You're going to have to put your calculator away. Okay? Do not use your calculator except for calculations. So get a calculator that just does calculations, right? Okay, but not a calculator that does integration or differentiation for you, all right? So that you can avoid the temptation, and do not log on to websites that will do this for you, right? Like Symbol Lab. You really have got to avoid that, okay? Because, well, it's just not going to work on a test. And so, well, you see the results, okay? So you know what scores you made, right? Okay. So I said that before, but now I think it's really clear for some of you. That's what you're going to have to do, right? Okay. And now I know also, again, be cautious about the other help, right, that's available in your homework. Don't rely on that exclusively for working your homework problems. I think that's less of an issue, though, than using a calculator or a website to actually solve the problem for you, okay? That is just really dangerous to your passing the course. I don't recall anything else that was that I had to say to you, other than, again, practice on, use the makeup test as an opportunity for practicing what you're going to have to do going forward to be successful in the course. Get help when you need it, right? Okay, so go to tutoring or come to my office when you need it, and then you're going to have to prepare for a test beyond just doing the homework, all right? You're going to have to prepare for the tests. Okay. But for those of y'all did really well, I congratulate you. So you've learned a lot, all right, in a very short period of time. So I had many excellent scores, many impressive scores on the test. I'd like to say the tests are going to get easier, but I don't. That's not going to be true. Okay, so I'd be lying to you. All right, it won't get easier, but you are going to get smarter if you do the things that I ask of you. All right, so it will seem as though the tests were getting easier. All right, because you're going to be just that much better. Okay, can you find who came in for me? All right. Okay, so if you came in late, Taylor's going to give you your test again. Remember this, right? The makeup opportunity, right? So read that announcement closely, right? In WebAssign. I wanted to show you one problem that Nicholas, right, asked me over the weekend, and we didn't give the answers like this in the notes, so I thought I'd better show you this one. It's pretty straightforward differential equations problem, so I think you can solve the problem the way we did in the notes, but then WebAssign writes the answer in a very seemingly unusual way. Okay, so it's really not that unusual, but we just didn't show it like this in class. Okay, so so we want to find, we want to solve this problem, right? We have the rate of change of this quantity P. I guess that's, you can think of that as a population, all right, of some creatures. And P is, the rate of change of P, is directly proportional to the size of P, right? So that's our typical setup, right, for our differential equations in the class. And so they're telling us, right, that when time is 0, that is the initial population is 6,000, but when time increases to 1, notice the population has decreased, right? So the population is going down to 5,100, and they just want to know what's the population when t is 4, right? So safe to assume, right, the population is going to be going down, right? But we want to find out exactly how much it is. So first, they ask us just to write down that differential equation, right? Can y'all remember those values for me? So when t is 0, p is 6,000, and when t is 1, p is 5,100, and then we want to know what's p when t is equal to 4, because I want to write this in the notes rather than writing it on the board. See if I've got some note paper down here that I can write on. Yeah. Okay. So it's easy to write down the differential equation. Easy to write down the differential equation, right? Because we've done this now several times, right? So the rate of change of the population, right, with respect to time, so that's dp dt, is proportional to the size of the population. So that means that this rate of change is going to be some constant of proportionality, right, times the size of the population, which is p, right? Remember, we're trying to write down the formula, right, for the population, and that's going to be a function of t. T is elapsed time here, but we have to solve this differential equation, right, to determine exactly what that formula is. All right, so we already know how to solve this differential equation, right? When you go through the steps of solving this differential equation, you are going to come up with a formula for p that looks like this, right? Because pretty much all of our differential equations, their solutions are going to come out the same. All right, so we'll end up with an exponential function, right, as for p. But now, so this is the answer to that first question on that problem, right? This is what the differential equation looks like, right? That's what the rate of change looks like. And now to write down the formula for p so that we can answer the second question, which is what is p when t is equal to 4, we need to figure out what c and also what the constant of proportionality is. And that's where the initial conditions they give us come into play, right? So they told us what? When t is equal to 0, p was, how much was it? 6,000, is that right? And your version of the problem will be different. But when t is equal to 1, p was equal to, was it 5,100? Okay, so we have to use this information to fill in the right values for c and k. Okay. Well, look, c is going to be the initial value, right, of this population. That's going to be the population when time is 0. So you can immediately fill that in. The c value is going to be 6,000. So you can plug that in rather quickly. Now, it takes a little bit extra work, right, to figure out what the k is. But this is where this second initial condition helps us. All right. So what we can do here is plug in 1 for t, and then plug in 5,100 for p in this equation, right? So we get 5,100 is equal to c, which we now know to be 6,000 from this information, times e to the k times 1, right? I'm going to plug 1 in for t. And then I have to solve this equation for k. That's just an exponential equation you're going to solve for k, right? So you were doing this on the test pretty easily. So you get e to the k is 5,100 divided by 6,000. And let's see, that reduces, right? Is that 17 over 20? Am I doing that right? I think so. Okay. So 5,100 over 6,000 reduces to 17 over 20. Now, just do what? Apply the natural log to both sides, right? So you get natural log of e to the k is the natural log of 17/20ths, but these cancel each other, right? Because those are inverse functions, so we have that k is the natural log of 17 over 20. Now, look, the thing that we were doing in class, and this is, in practice, this is what you would normally do, okay? You would use your calculator to estimate natural log of 17/20, okay? And then that's what, and you would have to round that off to a certain number of decimal places, right? And that's what you would use for k. What is natural log of 17/20 on your calculator to 3 decimal places? So what is that? Can you all compute that for me? Negative 0.162. Okay, so 63. Okay, so there's our estimate for k, right? Okay, and so in class, right, we would write down our formula for p as 6,000 e to the minus 0.163 t, correct? And that's perfectly okay. On a test, that would be fine. But now here's what. But here's how WebAssign wrote the formula for p. They wrote it a little bit different. So rather than giving a decimal approximation for k, they used natural log of 17/20. All right. Okay. So they plugged that in directly into this. They plugged that in directly into this formula. So they wrote down 6,000 times e to the natural log of 17/20 times t, okay? Now, they're going to break that up a little bit further. They're going to write that as 6,000 times e to the natural log of 17/20, and then all of that raised to the t power. Not the 6,000, but the e to the natural log of 17/20 raised to the t power. Why are these two things equal? Well, when you have a power, right, a power raised to a power, how can you simplify that? What can you do with the exponents here? Yeah, you multiply them, right, okay? So if you multiply t times natural log of 17/20, you get this, right, okay? So these two things are the same. All right, but the reason I wrote them differently is, what is e raised to the natural log of 17/20? E and natural log are inverses of one another, right? So what happens to them? They cancel, right? Okay, these things cancel, and so you get 6,000 times 17 over 20 to the t power. That's how they were writing the answer. Okay, like this. Instead of writing e, to this decimal value, they wrote it like this. It's the same, okay? Looks a lot different, but it's really the same. So we hadn't bothered to do that in class, but for some strange reason, that's how WebAssign decided to express the answer. Did anybody try typing it in like this, where you had 6,000 e to the natural log of 17/20 times t? Does it work that way? Does it grade it right? Oh, it does? Okay, all right, okay. Well, that's a relief then, actually, because this looks closer to what we, how we did it in class, right, than this, okay? This is more what I would expect on a test, or this is okay on a test, too, all right? In practice, this is probably what you would use, okay? A decimal approximation for k. All right. So anyway, just wanted to show you that if you were confused about that problem. Okay. All right. Are there any other questions there? That DE homework's not due till Wednesday, so you still have time to work on that. Okay. I don't know how many problems are on that. 10. Oh, so it's not terribly long. All right. So I think y'all can finish that easily by Wednesday. Okay. All right. Let's go back to the notes now, and let's finish up. Let's finish up the example we were doing last time about Newton's law of cooling, and then we'll be through with our differential equations examples. So you'll have a little bit of an idea of now how differential equations work, right? What they mean. For some of you, you have to take a whole course in differential equations. You're going to learn a lot more about how to solve differential equations, right, and how to apply them than we're learning in here. Okay, so so remember last time we were applying Newton's law of cooling to this problem. We had an object, and it was initially 100 degrees, right? And but we placed it in a room where the surrounding temperature was 60. So of course the object is going to cool off, and Newton's law of cooling tells us the rate of change at which that object is going to cool. Okay. This, by the way, Newton's law also applies, right? Remember, if you're heating up an object, okay. So if you place an object in an oven, for instance, right, where it's going to heat up, the same rule applies. Okay. So and we had a little bit of information about how fast the object was cooling. We're going to use that information shortly here. After we have finished solving the differential equation that goes with this problem. So what Newton's law of cooling says is that the rate of change of your object is proportional to something, okay, right? All the differential equations we've looked at, right, have that characteristic. But the rate of change in Newton's law of cooling is not just proportional to the temperature of the object, but it's proportional to the difference between the temperature of the object and the surrounding temperature, right? Which in this case was 60 degrees, because we placed this object in a cool location, right, a 60-degree room. So when we wrote down our differential equation, we wrote the rate of change is proportional to, there's our constant of proportionality, but it's proportional to the difference between the temperature of the object, which we called y here in this problem, and the surrounding, the temperature of the surrounding room. All right. So a little bit more complicated, not much, a little bit more complicated differential equation in the prior examples. In the prior examples, we would have had differential equations that look like this, right? Okay, we just would have had k times y. But in Newton's law of cooling, it's k times y minus 60, right? The difference between the temperature and the surrounding temperature. All right, so we wanted to solve this differential equation. But the steps are very similar to all the differential equations, all the previous differential equations examples, right? We're going to separate the variables first, right? So we want to get all the y's on one side and the in this case the t's on the other side, right? So I did that by multiplying both sides by dt, and then I divided both sides by y minus 60, so I came up with dy over y minus 60, that's all the y's on the left, right, is equal to k times dt, that's all the t's on the right. Actually, no t there, right, but there's a dt, okay? So there we have the dt on the right, and then to get rid of the dt and the dy, right, we integrated, right? We took the antiderivative of both sides, okay? So this is where we're testing our integration skills. This is an easy integral, though, right? Here you're just integrating a constant. K is a constant, remember, it's not a variable. The variable here is t. So when you integrate this, you're just going to get k times t, right? Plus, of course, some arbitrary constant. But on the left-hand side, this is where we get to use our integration skills. But we could have done this back, right, in the first week of the class. The antiderivative of dy over y minus 60 is going to be natural log of, actually, the absolute value of y minus 60, correct? So y'all all did that pretty easily on the test, okay? And then don't forget you have to add on a constant. Remember, I put subscripts on here just like in the prior examples because these two constants don't really have to be the same constant, right? Now, I dropped the absolute value bars because y minus 60 is not going to be negative because this object is cooling off to a temperature of 60 degrees. So this difference is always going to be either 0 or positive, right? It's not going to be negative. So you don't need to write the absolute values. That's a little bit of a relief. We got rid of the absolute values there. All right, so I think that's where we were last time. Let's see if we can finish solving. But these steps now are very familiar to us from our prior differential equations examples. So what do? Let's see. I'm going to bring this constant over, right, to combine the constants, correct? So I get natural log of y minus 60 is equal to k times t, and then you have plus c2 minus c1. But when you add c2 and c1, or when you subtract, right, c1 from c2, that's just another constant, right? So let's just combine those and call that c. So I have natural log of y minus 60 is equal to k times t plus a constant. And now, how do I solve for y? Do what? Yeah, raise e to both sides, right? Okay, because you've got to get rid of that natural log. So you apply the inverse, right, of natural log, which is exponential function. So we get what? Y minus 60 is equal to, and I'm going to split this up into two different parts. E to the kt times e to the c, right? Because when you multiply powers with the same base, you can add the exponents. But this is just a constant again, right? Okay, that's just e, which is 2.718 approximately, so that's a constant. This is a constant, so this is just a number, doesn't have a variable in it. So let's just rename that c again. There's no reason to write it as e to the c. That's just another constant. So almost done, and now just add 60 to both sides. So there is your there is the solution, right, to the differential equation. So nice, okay? So it looks like almost exactly right, like our solutions to our earlier differential equations, except that plus 60 is thrown in there right now, okay? Now let's see, now to actually answer questions here, I've got to figure out what is this and what is this, right? So what's the constant of proportionality and what is the C, okay? Be careful now. C is not quite what you're expecting here from the previous examples, because what's the initial temperature of this object when you put it in the room? 100. So you're thinking C is going to be 100, but that's not quite the case here, all right? Close, but not quite. So we know what? When T is 0, the temperature of the object is 100. So let's see what that means C has to be. So we get C times e to the k times 0 plus 60. But what's this? Is that just C? So we have 100 is C plus 60, which means, I guess, what? C here is equal to not 100, but 40. All right? So in our formula, this is going to be 40. Now let's see if we can figure out what K is. So let's see. When how do we figure out what K is? When T was, what other information did they give us? When T is 10, right? They told us the temperature had dropped to what? What was it? I forgot. Yeah, let's read back there. Yeah, after 10 minutes, so it took it a little while, the object had dropped 10 degrees. This thing is not cooling off very rapidly because it took 10 degrees for it to cool off. So that might be some really thick object, right? Like a baked potato or something like that, okay? Well, but in any event, whatever it is, that's all the information we need, right? So the temperature is going to be 90, right, when T is 10. But we already know that C is 40, so we can plug the 40 in for C, e to the k times 10 plus 60. And now you've got this equation to solve, but now for K. But we're pros at solving this equation, right? Subtract 60 from both sides. So you get 30 is equal to 40 times e to the 10k. And then do what? Divide both sides by 40 first. So you get 30 over 40, which I guess is 3/4, is equal to e to the 10k. And now take the natural log of both sides, right? So we get 10k is natural log of 3/4, which means k there is the natural log of 3/4 divided by 10. What's that approximately? So I need a decimal approximation for that. It's easy to divide by 10, so just what's natural log of 3/4? That's going to be negative. Did y'all get that? Someone who has their calculator. You got to tell me. Everybody's writing it down, but I need to know also because I can't write it down. What is it?
-0.02.
So -0.029 minus 0.029. Okay. So finally now we can write down the complete formula. Let's do it up here. Let me erase this. Let me erase this arrow. So C was 40, and E is approximately I'm sorry, k is approximately minus what, 0.029 times t plus 60. And now that's the cooling formula for this particular object, right? 40 times e to the minus 0.029 times t plus 60. And now you can use that to answer any questions you want, right, about the temperature of the object, correct? So if you want to know when it reaches, when does it reach what, 80? Is that what it asked there, right? Okay, then just plug 80 in for y, right? Okay, plug 80 in for y and solve that equation, okay? So y'all know how to do that, right? Plug 80 in for y and then solve that equation. You're going to solve that eventually by applying the natural log to both sides, right? But you have to do a little bit of arithmetic first before you apply the natural log to both sides, okay? So I will leave that to you guys to solve that final equation, which is this one. Y'all are good at this now, so, well, pretty good at this. There's a problem very much like this one on the test. What problem is like this one on the test? It's number 5, okay? That was a cooling problem, wasn't it? And I believe the last part of that was, so you didn't have to solve a differential equation, okay? Oh, number 6? Yeah, all right. So you didn't have to solve a differential equation to get that formula. It was given to you, right? Okay. So there's a formula that looks very much like our formula, correct, that we came up with. And you were asked to determine when that object got to a temperature of, what was it, 130? This object is heating up instead of cooling off, I think. Okay. So most of y'all, that was part C. Most of y'all did that pretty well, okay? That certainly wasn't the most missed problem on the test. That problem number 6, though, was frequently missed, especially the first part, okay, where you're just computing the derivative. That should be easy, okay? That's derivative of an exponential function. That's pretty easy. So that's why I listed that as you know, one of the problems to prepare for the review, okay? So if you've done your differential equations homework, then you're way beyond that problem number 6. You've done much harder things than that already, okay? So if you finished your DE homework by that makeup test on Wednesday, you should be prepared for that problem at least. Okay. All right, so much for differential equations. We just get to get a brief introduction to that, and now we're going to go on to another application of integration. Now, look, we're going to have to do some heavy lifting today. This is going to be quite conceptual at first, okay? But once we get past the conceptual part of the explanation, the actual applying the concepts turns out to be not really that difficult, okay? So bear with me, stay engaged with me, pay attention to what and try to understand what I'm telling you, okay, at first, so that you can derive the benefit of that when we get to the actual problems that we're going to solve, okay, because the explanation will make the solutions to the problem much easier, okay? All right, so let's launch into this. Okay, so this is what I promised you earlier. We have to now review here a little bit about what we mean by definite integration. Okay, so that's where you're, computing an integral where you have upper and lower bounds, right, on the integral. And when you evaluate it, you get a numerical answer, right? You don't get an antiderivative, but you get a numerical answer, correct? Okay. Now, it's the fundamental theorem of calculus that allows us to compute easily definite integrals. Okay. And the fundamental theorem of calculus is so powerful that we forget what definite integration really means, because the fundamental theorem makes it easy to compute, well, at least in theory, it makes it easy to compute definite integrals. All right. So let me remind you of the fundamental theorem of calculus, but you're very familiar with it. Okay. All right. So here's what the fundamental theorem of calculus says. Suppose that you have to start off with a continuous function on some interval, right? And suppose you want to compute the definite integral of that function, the definite integral of that continuous function, starting at A and going to B, right? Okay, so you're evaluating a definite integral. Well, you know how to do that because we practiced this already many times in the class, and we did it on the test, okay? I mean, you did this on the test too, right? So 3 of the problems on the test were, actually more than 3, I think 4 problems on the test were computing definite integrals, right? Okay, which problems were those on the test? One of them was number 9. And then I think the problem directly before that, 8, A, B, and C, okay? Yeah, those are all computing definite integrals, right? So, and you do this a lot in Calculus 1, right? So, so how do you compute a definite integral, right? Remember, what do you have to find from f? You have to find its antiderivative, correct, right? So, to compute a definite integral, you have to find the antiderivative for f, little f. I called that capital F in this equation. So capital F is the antiderivative of little f. And then you just plug the upper and lower bounds, right, into the antiderivative and take the difference, and that's it. Voila, okay? You have the, you've evaluated the definite integral, okay? So, that's what the fundamental theorem of calculus tells you, all right? It tells you this process, right, for computing a definite integral. And that's really easy to apply. Well, of course, there's a catch there, right? Sometimes it's not so easy to find this antiderivative, right? Okay? But once you find the antiderivative, then it's easy then to finish evaluating the definite integral, okay? All right, that's all courtesy of fundamental theorem of calculus. But because that process is so easy to remember and often so easy to apply, it makes you forget what you're really doing when you're setting up a definite integral. What does a definite integral really mean? Okay, it does not mean this. Okay, this is just the process that we use to evaluate definite integrals, but this is not where definite integrals really come from. Okay, that's not really the definition of definite integral. This is just a tool we use to make it easy to calculate definite integrals, but this is not where definite integrals, what definite integrals really mean. Okay, so we have to go back now a little bit, and I have to explain to you, what are you really doing when you're computing a definite integral? What does that really mean? Okay, it's easy to do with the fundamental theorem, but if you didn't have the fundamental theorem, how would you compute a definite integral? Okay. What is that indicating? All right, so here's what definite integration is really doing. Okay, when you are setting up a definite integral, okay, when you are setting up a definite integral, what you are doing is you're taking a quantity, okay, some quantity, could be a volume or it could be an area under a curve or some other quantity, right? And you're trying to measure that quantity, all right? But for some reason, so definite integral gives you a measurement of a quantity. But for some reason, you are not able to directly measure that quantity, okay? For some reason, that quantity is difficult to measure directly, all right? So you're going to have to, if you want to measure it, then you're going to have to do it indirectly. So there may be other ways of measuring that quantity indirectly, but here's the idea behind definite integration. What definite integration does is it says, okay, we're going to take this this big quantity that we're trying to measure that's hard to measure for some reason, and we're going to break it up into smaller pieces. We're going to break it up into smaller pieces, a bunch of small pieces, all right? And we want to break it up into small pieces so that the small pieces are easy to measure. Okay, the small pieces are easy to measure. So we take the big quantity that we're trying to measure, we break it up into a bunch of small pieces, hopefully that are easy to measure. Okay, we measure all the little small pieces, and then we add them all together, and that gives us a measurement for the big quantity, right? It's just a divide and conquer strategy, right? Okay, we're going to take this big problem, we're going to divide it up into smaller problems. and solve the smaller problems and then combine our solutions to the smaller problem to get the solution to the big problem. This is a very typical problem-solving strategy in not just in mathematics, but in life in general, okay, right? Okay, now let's take an example then of such a situation, okay? And here's the classic example that you're taught in Calculus 1, all right? So what I have in the notes here is what I just said, okay, in words. All right, so suppose now I have this problem given to me, okay? All right, I want to compute, right, the area beneath this curve, 1 over x plus 2. I want to compute that area, right, down to the x-axis beneath this curve, down to the x-axis, starting at x equals 0 and starting at x equal 3. All right, so the quantity that I'm trying to measure here is this area. Okay, that's the big quantity that I'm trying to compute. The area beneath that curve, 1 over x plus 2, down to the x-axis, starting at x equals 0 and going over to x equals 3. All right, so you can maybe visualize this a little bit in your mind, but actually let's draw a picture of it so it's easier to visualize. I have to scroll down in the notes here, right, to see a picture of this. It's way down here, but it's somewhere. Not there. Oh, there it is, okay. All right, so this is the curve. So that curve is 1 over x plus 2. Was it 1 over x plus 2? All right. So there's the curve, 1 over x plus 2. And I want to find the area beneath that curve, right, down to the x-axis, right? So this is that shaded area, starting at 0 and going over to 3. So that's really a geometry problem, right? Okay, that's a geometry problem because we're computing the area of a region. Okay, that's the sort of thing you do in geometry. But this region is difficult to, with just your knowledge of geometry, right? This region is difficult to calculate the area of. Why? It's not a particular shape. That's right, yeah. It's not some regular shape that you learn how to compute the area of in geometry, right? What sort of things do you learn to compute areas of in geometry? Oh, I don't know, you know, rectangles, right? Circles, right? Very nice, simple, regular shapes, right? You learn to compute areas of. You might learn some exotic formulas like area of a trapezoid, okay? But mostly, you know, it's very simple things like rectangles and circles, correct, right, that we know how to directly compute the area of, and this is not any of those things, all right? So that's what makes the computing the value of this quantity hard, okay? So we have to go to plan B, right, because I don't have a formula from geometry, right, to compute the area of that region. So in this case, my plan B is going to be definite integration. What I'm going to do is take that quantity, that area, and I'm going to break it up into some small pieces, okay? I'm going to break it up into small pieces. I'm going to try to measure the area of those small pieces and then add all those areas back together to get the area of the entire region, okay, right? So it's just this divide and conquer strategy. Now, however, the small pieces that I break the area up into, I have to make sure that I can measure their areas, okay? So I have to break this up into pieces, into geometric shapes that I know how to measure the area of, right, okay? So I guess I could break this up into a bunch of circles, right, okay? But, because we know how to measure the area of circles, right, okay? But that's not really the way we're going to go here, right, okay? What's maybe a more convenient way? Yeah, I'm going to break this up into a bunch of little rectangles, right, okay? So I'm going to try to break this area up into a bunch of little rectangles, right? Calculate the area of each of the rectangles, correct, right, okay? which I know how to do from geometry. That's easy. We have the area of a rectangle formula, right? And then add all those areas back together, right, to get the area of that under that curve, okay? So that's exactly going to be my strategy. This is definite integration, almost, okay? It's at least the start of definite integration, all right? Okay, well, let's draw a picture of that, of doing that, okay? So let me scroll back up here to the notes, and let me show you what the picture that I drew, okay? So that's that same curve, and so what I've done is I've broken that area up into, in this case, 6 rectangles. The number 6 was completely arbitrary, okay? I just chose 6. I could have chosen more rectangles, or I could have chosen fewer rectangles. I'm just going to start with 6, okay? So there are my 6 rectangles, all right? And I'm going to calculate the area of each one of those rectangles. I'm going to add those together, and I'm going to use that as the area for that region beneath the curve. Now, I'm going to be off by a little bit, aren't I? Okay? Because when I compute the area of these 6 rectangles, of course, I know how to do that from geometry, right? When I compute the area of these 6 rectangles, I'm going to miss the area, the correct area under that curve, right? Because the rectangles don't perfectly fit into that area, right? Okay? You know, sometimes I miss a little bit, right, okay, when I'm drawing the rectangles, or sometimes I put a little bit too much in there, right, okay. This rectangle's, you know, goes a little bit outside of the area beneath the curve, right. So, so I'm not going to get a perfect, you know, a value for the area beneath that curve, but I'm going to get an estimate at least, right, okay. And it looks like it's probably going to be a pretty reasonable estimate for the area beneath that curve. All right, so let's write this process down then, okay? Let's write this process on what we did, okay? So I broke the area up into 6 rectangles, right? Okay, and notice I picked the rectangles so that they all had the same width. That's just going to make my calculations easier. The rectangles, though, do not all have to have the same width. That's not a requirement. But it does make the computations easier. So I picked all the rectangles to have exactly the same width. Notice, though, the rectangles, of course, are not going to have the same height, right? Okay? There's no way to make them have the same height. All right, so let's start writing down some of the areas of those rectangles. Okay, so we got to keep very careful track of our work, or we're going to get lost here because there's lots of calculations involved in, you know, computing the areas of those 6 rectangles, right? Okay. All right. So I'm gonna introduce a little notation here. All right. So you know, so when I'm breaking the area up into rectangles, I have to pick the number of rectangles that I wanted to use. I chose that to be 6. Okay. I chose that to be 6 at least to start with. All right. I'm going to call that value, the number of rectangles, I'm going to call that n. All right. But in this example, n happens to be 6. All right. Now, of course, each of these rectangles has a width, right? And I'm going to pick the rectangles so that they all have the same width. That makes the calculations easier. So let's see, what would the width of each rectangle be? Well, let's see, what was the total length of that area? We were going from x equals 0 to x equal what? 3, right? So that total length is 3 minus 0, or 3, right? And I broke that up into 6 rectangles. So the width of each one of the rectangles is going to be 3 divided by 6, 3 divided by n. And that gives us 0.5, right? Okay, duh, that's obvious. I'm going to call that delta x. So that means the width of each rectangle, okay? All right, now let's see. When you're finding the area of a rectangle, you need the width of the rectangle, right? But you also need what? The height. Now, unfortunately, as I mentioned, all the rectangles will not have the same height, right? Okay, because as you're going from left to right, that curve gets lower and lower, so all the rectangles won't have the same height. Okay, all right. So how am I going to decide what the height of each rectangle is? All right. Well, here's what I'm going to do. Okay, from the width of each one of those rectangles, I'm going to pick a value off of the x-axis. All right. It can be anywhere in the width of the rectangle, though. Okay, I'm going to pick a value off of the x-axis. So for the first rectangle, that value that I pick off the x-axis, I'm going to call that x of 1. I don't know why I put an asterisk here. It just made me write a bunch of extra stuff, but it's there, all right? So this is a value on the x-axis, but in the first rectangle, This is a value in the second rectangle on the x-axis, and so on and so forth. So the subscript means where the x, in which rectangle the x is located. But remember, the x's are always on the x-axis. Let me show you that picture. So let's go back here to see that picture. So you see what I did there? There's x1. I just picked a value in the first rectangle on the x-axis. But let me point out, you could have picked that x1 anywhere. So it could have been further to the left, or it could have been further to the right. It doesn't really matter where I pick it. I picked it kind of close to the middle, but you don't have to pick it close to the middle. It can be anywhere, all right? So this is kind of an arbitrary value, but it does have to be in the first rectangle, so it has to be between 0 and 0.5, right? Okay. Now, I'm going to use that to help me compute the height. How? All right. Well, starting here, starting wherever I pick this x1, I'm going to draw up to the curve. And that's going to be the height of my rectangle. So start here on the x-axis at this value on the x-axis. Remember, you just pick that anywhere between 0 and 0.5, and draw up to the curve. Okay, that's going to be the height of your first rectangle. What is that height? No, I don't know if that's 0.5 or not. Okay, might be. Okay, but how can I compute that height? See, you're going from here up to the curve. So what would that distance be? Remember, there's a formula for this curve, right? What's the formula for this curve? Plus 2, right? 1 over x plus 2. So what's this height have to be? Yeah, plug this into what? Into the function, that's right, okay? Plug this into the function. So take this quantity, whatever x1 you picked, plug it into the function, and you'll get this height, right? Okay, you'll get this height. So how do you, Janai, how do you indicate when you plug a value into the function? Yeah, what do you write there? You just write what? Yeah, right. Okay, so this is 1 over x1 star plus 2, right? Better known as f of x1 star. That's what I was trying to get you to say, right? Okay, yeah. All right, because the formula for f is 1 over x plus 2, right? Okay, so there's the height of that first rectangle. It's this. It's f of x1 star, which happens to be this amount, right? Okay, according to that particular function. Well, you're going to do the same thing for every rectangle. So go to the second rectangle, pick an x value out of that second rectangle. Make sure you're on the x-axis. It can be on the right or it can be on the left. You don't care. Then draw up to the curve, and that's going to be the height of your second rectangle. So, of course, that height is what? That's f of x2 star, right? Okay, and so on and so forth, right? So you do the same thing for all 6 rectangles. In the last rectangle, notice I put that x6 all the way on the right-hand side. That's fine, okay? As long as it's in the rectangle. It couldn't be over here, but as long as it's in the rectangle, it can be on the right side or the left side or right in the middle or anywhere in between, okay? That doesn't matter. All right, so we've got it, right? We know the width of each rectangle was, what was it, 0.5, right? Okay, and now we know how to compute the height of all the rectangles, right? We have to pick off these 6 values, right? But once those are picked off, you know how to compute the height of all the rectangles. Multiply the width times the height, add them all together. You're going to get the area of all those rectangles added up, right? So what does that look like when we do all those? What does that look like when we do all those calculations? It's going to look like this, right? Ugh. Okay, all right. So there's the height of the first rectangle. There's the width of the rectangle, right? There's the height of the second rectangle. There's the width of the second rectangle. There's the height of the third rectangle. There's the width. Height, width, height, width, height, width. Add all those together, and that gives you an approximate value for, only approximate, right? But we think it's pretty close, but only approximate value for the area beneath that curve, okay? All right, now, that's a lot of terms in this sum, right? You're adding a lot of things together. So that's kind of a big, messy expression, adding all these together. So we have a shorthand for this, okay, that will make it easier to write down this big sum. Let me show you the shorthand notation because it's really convenient, and we're going to come back to it later in the semester. See that giant? That's the Greek letter sigma, right? Okay, you know that from fraternities, right? That's or sororities. That's the Greek letter sigma. So we use that to indicate a sum, sigma for sum, all right? And notice that in this sum, right, all the terms in this sum look identical, except what's the only thing that's changing? Yeah, the subscript on the x, right? Okay. Otherwise, all these terms are alike. So you can collapse that big sum into this notation. Here's what this notation says. I'm going to add a bunch of things together. They all look like this, okay? It's a height times a width, right? But how's the height computed? Well, you change that from starting at 1 going up to n. What was n? 6, right, okay? So your first term is going to be f of x1 times delta x. Your second term is going to be f of x2 times delta x. Your third term is going to be f of x3 times delta x, up to your last term, which is f of x6, right, times delta x, okay? So that's just a convenient shorthand notation for that big sum, okay? For those of you who are computer scientists and are programmers, right, you know that kind of looks like a loop, right, okay, where you're changing the index of the loop. Yeah, this was kind of loops before computer science existed, okay? They were expressed using this kind of notation sometimes. All right. Now, we're not actually going to do these calculations, okay? We saw a picture, sort of, though, of the calculations, right? Because we saw all of these rectangles, and we were thinking, okay, you know, that's probably a pretty good estimate, right, for the area beneath this curve, but it's not going to be perfect, right? Not going to be perfect, so I want it to be perfect. Now, so far, though, notice we have not used any calculus. This has all been arithmetic, not even algebra. This has all been just arithmetic and very crude geometry, right? Just area of a rectangle, okay? And a little bit of algebra, maybe, okay? For that function notation, that's a little bit of algebra. But no calculus has been involved here at all, all right? So this is all stuff you could have done before you got to calculus 1, all right? But now here's where the calculus is going to come into play. Look, this is only an estimate, right, for the area, correct? So this is only an estimate for the area. I want, though, to calculate the area exactly. So how do I get a better estimate for the area? So what can I change to get a better estimate for the area here? Let me show you the picture again. So we estimated that area using these rectangles. How could I get a better estimate for that area? Yeah, Pedro? More rectangles, that's right. Yeah, more rectangles, okay? So increase the number of rectangles, right? Okay? Intuitively, that makes sense, correct, right? If you increase the number of rectangles, notice the rectangles are going to get thinner, right? Thinner, and they're going to start representing this area a lot better, a lot more closely, right? They're going to fit into that area more closely. So Pedro's right. We can get a better estimate by increasing the number of rectangles, okay? We can just increase the number of rectangles. So what was I calling number of rectangles? N, right, okay? So here I was using n equals, what was it, 6, right? Okay, so here I was using n equals 6, but there's no reason to stop with 6, okay? We can increase this to 100, for instance, right? Okay? Notice that doesn't really change very much in all the stuff that I have written down, okay? What does the delta x become there? What's the width become? Well, you still have 3 over n. What's 3 over 100 now, though? Is that 0.03? Yeah. So the width changes, right? Okay. But notice this expression, you don't need to change at all, right? Okay. You don't need to change this expression at all. What's changing in this What's changing in this expression? Yeah, the n now is, instead of going from 1 to 6, we're going from what? 1 to 100. And what's the delta x here? What did I say there? 0.3, right, okay? 0.3. You'll still compute the heights in the same way, except you'll have to compute now 100 different heights, right, okay? But you don't have to rewrite anything. All that information is still expressed in this expression. Okay, so Pedro, when I go up to 100 rectangles, I'm going to get a lot better estimate for the area, but still, that's still going to be an estimate. Those rectangles are not going to perfectly fit into that area, okay? So how do I get a better estimate? Well, let's take it slowly here, all right? So you may want to increase what? Your number of rectangles to... Oh, wow, come on. 1,000. All right, yeah, y'all are being... don't want to be a wimp there, right? Go up to 1,000, right? Okay. So now what does the delta become there? Is that 0.003, right? Okay. But notice now, I don't have to rewrite this, correct, right? Okay. All I know is that this number is now larger and this delta is smaller. But this expression still represents the area. Okay, Pedro, you had the right idea. We still haven't used calculus, though, right? Okay. Because I've just increased the number of rectangles. It's going to be a lot of adding, right? Okay, a lot of arithmetic to increase the number of rectangles to 1,000. If we want to do that by hand, we would be here for a long time, right? Okay, but when n goes to 1,000, when the number of rectangles goes to 1,000, that does give us a better estimate, but still not perfect, right? Okay, still not going to be a perfect estimate. Now, but you have the right idea. So what would calculus say? Calculus would say, just what you said, Pedro. Why are we fiddling around with 100 and 1,000? We might as well go all the way to what? Infinity, right, okay? We might as well think about increasing our number of rectangles to infinity. If we increase the number of rectangles to infinity, that will give us a perfect representation. That infinity many rectangles will give us a perfect representation for the area under that curve. Now, infinity, unfortunately, though, is not a number. So you cannot say n equal to infinity, okay? So what's calculus's compromise? Calculus doesn't say, I'm going to plug infinity in for n right here, right? Okay. Oh, by the way, if n was infinity, what would the width of each of the rectangles be? You would know. It would be 0, and this would all add up to 0, right? Okay. So you cannot plug infinity directly in for this value n. Infinity is not a real number, right? Okay, so you can't plug infinity in directly. But so what's the compromise in calculus? What's the game that we play in calculus when we want to do infinite calculations like this? Limits, right? Okay, yeah, this is where we exploit the notion of limits. So you don't actually let your number of rectangles equal infinity. You simply ask, what is this quantity going to be, right? Okay, what is this sum going to be as what? As n approaches infinity, right? Okay, what's the limit of this sum as n approaches infinity? That is going to be our exact value for the area. Cool, right? Okay, see how calculus allows us to work with infinite quantities indirectly, right? So here, here's our exact value for the area, right? It's the limit as n approaches infinity, right? Okay, of this big sum. That's still a lot to write out, okay? That's still a lot to write out. So mathematicians are lazy. They do not want to write all of this out like this. So what they have done is they have devised a more compact notation for this limit. And you know what that more compact notation is. It's this. That's what a definite integral really means, okay? All right? It is a shorthand for, a limit of this sum as the number of terms in this sum becomes infinitely large, okay? So this notation is due to Leibniz, the French mathematician. He said, I'm tired of writing down this limit and this delta and this big sigma here, so I'm going to replace that with just this stylized s, right? Okay? And then express all of this, right, in the familiar integrand fashion. Oh, by the way, let's actually compute this now, okay? This is where the fundamental theorem helps us, right? Okay, so I don't have to, I don't have to try to actually, compute this sum and then try to figure out what the limit is as n goes to infinity, okay? Because the fundamental theorem of calculus tells me how to compute this limit, okay? Right? That's the great thing about the fundamental theorem of calculus, the real time saver. The fundamental theorem of calculus says, what do I need to do here? I need to just find what? Antiderivative, right. I just need to find the antiderivative of this function f. Oh, by the way, let's fill that in. So we have what? The definite integral from 0 to 3 of 1 over, what was it, x plus 2, right? I've already forgotten, okay? And but what is that? What is the antiderivative? So you know this now. There you go. It's natural log of x plus 2. Yay! So it's just the natural log of x plus 2, and we're going to evaluate that from 0 to 3. Okay? So we get here what? Natural log of 3 plus 2, right? Minus the natural log of 0 plus 2. So that's the natural log of 5. I don't need the absolute value bars because that's already a positive number. Minus the natural log of 2, right? And you can rewrite that. That is the natural log of 5 halves, right? Okay? Remember, when you take difference of natural logs, you can write that as natural log of a quotient. So there is our area exactly. It's natural log of 5 halves. What does the calculator say that is, by the way? What is it? Natural log of 2.5 is how much? 0.916? Yeah, that's, I bet that's right, okay? Pretty close. Yeah, because 5 halves is 2.5. That's pretty close to E, though, because E is 2.7. So this is almost the natural log of E, but natural log of E is 1. So indeed, it is going to be pretty close to, the answer is going to be pretty close to 1, about 0.916, okay? All right? Cool, right? So that is exactly the area under that curve, all right? Now, my goal here is to not reacquaint you with the fundamental theorem of calculus because you've used that lots, all right? So you know how to get from this definite integral to the answer. But I just wanted to remind you, what does that definite integral really stand for? It stands for this sum, okay? It's a limit of a sum as the what? The number of terms in the sum goes to what? Infinity, right, okay? That's what definite integral really means, okay? All right, now with that little refresher, we're going to apply that same idea, that definite integration idea, to a different problem, okay? Not area under a curve, all right? But a similar geometric problem, okay? So it'll be quite analogous to, quite similar to area under a curve. All right, we better stop there for a few minutes, okay? And then we'll come back and we'll show you how to apply the same idea in a little bit different problem, okay? Of two things. The points you get on that makeup out of the total that are available there, and then what your test score was. So it's a little bit complicated formula to know exactly what, how many points you could add. All right. So because it depends on your test score. So the lower the test score, potentially more points you could get added back, more makeup points you could get. Okay, that's why I mentioned for someone who had a very close to a 100, for those people who were in the 90s, even a perfect score on the makeup will not really earn you many makeup points. Okay, because you cannot, there's no way to get your score adjusted above 100. Okay, so it's less beneficial if you're already in the 90s to take the makeup, but it's more beneficial the lower your score was. Okay. However, it won't. It's not the case that if say someone made 50 on the test and someone made 60 on the test, they both took the makeup. And they both earned the same number of points on the makeup. It's not possible then for the person with 50 to surpass the person with 60, right? The rank, the order of the students will remain the same. Okay, yeah, that makes sense, Christopher. Yeah. So if you took the makeup and both people did, someone made it 50 and someone made it 60, if you both did equally well on the makeup, then the person with the 50, they'll have points added, and the person with 60 will have points added, right? But the 50 person cannot surpass the person that made a 60. Okay, you will still have a higher score, unless, of course, the person with 50 made a really good score on the makeup, and the person with 60, did bad on the makeup. Then the orders could flip. All right. Okay. So the answer is I can't give you a firm response to that. All right. Okay. All right, so let's look at our next application here and see if we can get to the formula that I want to get to. All right, so in this example, this looks like initially like area under a curve, but it's not area under curve. But it starts with an area beneath a curve, right? Okay, so we have this area beneath this curve, square root of sine of x. So that's kind of a strange curve to be working with, square root of sine of x, but it's kind of a made-up example just to make the eventual computations simpler for us, all right? But there's what square root of sine of x looks like, at least from 0 to pi. It's not a semicircle, but it looks elliptical, right? I don't think it's even an ellipse, but it's got kind of like a semi-ellipse, right? Similar to that. And so here's there's the area beneath that curve down to the x-axis, but that's not what we want to compute. We know how to compute that, right? You just use this definite integral, right, to calculate that green area, okay? But here's what we're going to do. We're going to take that green area, so you have to use your 3D imagination here a little bit. We're going to take that green area and we're going to rotate it all the way around the x-axis, 360 degrees, all the way around the x-axis. All right, so keeping this part on the x-axis, right? So keeping the bottom portion of the area on the x-axis, you're going to rotate the top part, right, all the way around the x-axis 360 degrees. So back to this position. So when you do that, of course, that sweeps out a volume, correct, right? Okay, that's going to sweep out a volume. And what we're trying to compute is that volume. What is that volume? So let me show you a picture of that volume. So I show you a 3D picture here. Let me scroll down to find it. Way down here. There it is. Okay. So see, it's got kind of this football shape to it, right? Okay. So there's that purple curve there. That's square root of sine of x, and so we've taken that area beneath that purple curve, right, and rotated all the way around the x-axis. So you get this shape, right? And we're trying to calculate the volume of that shape. So we're in much the same situation as we were in just our previous example, where we were trying to calculate an area, except this seems a little bit harder, right, because it's a volume instead of an area. But we're in the same situation because we don't have any geometric formula that applies here, right? Okay, so we do have some geometric formulas for volumes of some solids, like a cube, right? We have a geometric formula for the volume of a cube, or a sphere. We have a geometric formula for the volume of a sphere. You probably don't have at the on the tip of your tongue the formula for the volume of a sphere, but you can look it up easily. And also, you probably used it before. You just probably don't remember it. And maybe volume of a cone, right? Okay. We have formulas for volume of a cone, and maybe a few other geometric shapes, volumes, three-dimensional shapes, but not too many. Okay. And that certainly is not. We don't have a ready-made formula for that volume. So we're going to have to do it the hard way, right? Okay. We're going to have to try to compute it directly, right, without from scratch, without having a nice formula from geometry. All right, so we have to have a plan of attack here, right? We have to have a problem-solving strategy, and indefinite integration is going to be it, okay? Because what we're going to try to do is, just like with the area, we want to take that volume. That's a big amount that we're trying to calculate, right? That's a big quantity that we're trying to calculate, and we want to break it up into smaller quantities, smaller volumes, hopefully that we know how to compute, and then add all those smaller volumes together to get at least an estimate for the big volume. All right. So somehow I've got to cut that football into pieces, right? And hopefully it'll be pieces that I can measure. The volume of each of the pieces, and then add all those volumes together to get at least an estimate for the total volume of the football. All right, so that's the strategy. That is the definite integration strategy, right? Now, however, this is the big question. This is the hard part of definite integration, really, is what are the pieces going to be? So what am I going to break this up into? Okay, right? Because I've got to break it up into pieces that I can compute the volumes of. Those pieces are going to be three-dimensional things also, and again, I don't know how to compute the volumes of many three-dimensional things, so I have kind of a limited repertoire here that I can draw from. Any suggestions of how you might want to cut this up? Well, yeah, circles, but circles are two-dimensional objects, right? Okay, so a bunch of little spheres. So yeah, well, you could, I guess. I can't even draw that very well. All right, I guess you could try to fill that up with balls, right? Okay, but that would be kind of like filling the area up with circles. I mean, I can fill it up with balls, with spheres, but I'm going to have a hard time. Figuring out how to add all those spheres back together in a systematic way to give me the volume of the entire football there. So I need something kind of similar to, how easy it was to break the area up into rectangles. So is there some way to break this volume up into some figure that, some 3D figure that I know how to compute the volume of and really fits nicely into the football there, okay? Any ideas there? No ideas there, no. It has to be a volume, right? I've got to add all those volumes together to get the volume of the original thing, right? Of the volume of that. All right. Y'all just waiting me out here. Very distressing in a way. Okay, well, here's what I'm going to do. All right. The very obvious choice, okay? I'm going to break that football into, what have I broken that up into? Cylinders, right? Or these are really flat cylinders, so I'm going to call them discs. Yeah, I'm going to break it up into discs or indeed into cylinders. All right. So in a way, I'm just kind of slicing that from left to right. Okay, like a big slab of bologna there, right? I'm just going to slice that up into these discs, okay, or cylinders. Okay. How many cylinders did I try to slice that thing up into? 5, right, okay? So I tried to break it up into 5 cylinders. Notice the cylinders don't fit perfectly right into the football. You can't perfectly fit 5 cylinders into that football so that, the cylinders fill up the football. There's no way to do that, right? But if you can calculate the volume of those 5 cylinders, right, you'll at least have an estimate for the volume of the football, okay? Your estimate's off a little bit because this cylinder doesn't quite fill up its piece of the football, right? Okay. Whereas this cylinder on the right end, right, that's a little bit maybe too large, right? Because there's a piece of a large chunk of this cylinder, right, that's outside of the football. But altogether, if we could compute the volumes of these 5 cylinders, right? Okay. That would be a reasonable estimate, at least as a start, right, for the volume of the football. Of course, now with calculus, then what are we going to do once we have done that once, right? Once we've calculated the volume of those 5 cylinders and sort of got that under our belt, then how are we going to improve our estimate? Well, so we're going to start by, before we jump to infinity, we would start by what? Going from 5 cylinders to 10 to 100 to 1,000, and ultimately we would say, well, let's skip past all this and just do what? Well, yeah, but before the integration, though, we would take the limit, right, as what? Gets infinitely large. Well, n, but so what is n representing? Yeah, it's the number of cylinders gets infinitely large, right? Okay, so we would try to write down some a formula, right, for adding up the volume of all those cylinders, correct? All those disks, and then we would think about, well, what happens to that formula as the number of disks goes to infinity, correct? Right? Okay, and if we can compute that limit, then we'll be in great shape, right? We would then know the volume, the exact volume of the football. All right, so to write down that sum of the volumes of all those cylinders, well, we got to get a handle on that problem. So let's try doing it. What do you need to know to calculate the volume of a cylinder? So this is probably already something not immediately familiar to you, right? But how do you calculate the volume of a cylinder? All right. Well, let me remind you from geometry how that's done. Okay. I called it a disk here. A disk is just a really thin cylinder. Okay. Same thing as a cylinder. All right. So there's a disk, right? Okay. Just a really short cylinder, right? Okay. And actually, the formula for a volume of a cylinder it should be kind of familiar to you because it's actually very similar to volume of a cube. Okay. Volume of a cube. What you do is first compute the surface area of one side of a cylinder. Of course, one side of a cylinder is really a what? A circle, right, okay? So the surface area of one side of the cylinder would be the area of the circle on that side. And, well, we know how to compute area of a circle, right? That's what? That's circumference. But area of a circle is what? Pi r squared, right. So just take their pi r squared. That would give you the area of that of the top of that cylinder, and then all you have to do is multiply that area by the width. Okay, just multiply this area by the third dimension, and which is the width, and that gives you the volume of the cylinder. It's a really straightforward formula. It's just like how you compute the volume of a cube, right? Okay, it's just like how you compute the volume of a cube. Actually, it doesn't have to be a perfect cube. It can be just a box. Let me see if I can draw one here. Probably I'll screw it up, but yeah, there's a box, right? Okay, and of course, how do you compute the volume of a box? It's length times width times height, right? Okay, right. So let's think of this though as being the height. Okay, so see what you're really doing is you're computing the area of one side of the box, right? Which is, and what's the area of that? Length times width, right? And then you just multiply that area times the third dimension, right? Times the height, okay? That's exactly what you're doing in the cylinder. You're computing the area of one side of the cylinder and then just multiplying it by the third dimension, okay? That scheme often applies to compute volumes of objects, okay? Unfortunately, it doesn't work quite on the football, right? But it works nice on the cylinder, right? So there's the area of, so all of those disks, their areas can be computed this way. So it's going to involve pi, but we have to know the radius of every disk, and we have to know the width of every disk, right? Now, the width of every disk, though, that's pretty easy, okay? Because what's that total length there along the x-axis of the football? That's pi, right? Okay, so we have the width of every disk would be pi minus 0, that's pi, divided by the number of disks, and I'm going to call that n here, and of course in this example that's what, 5, right? So the width of every disk is pi divided by 5, okay? Let's give that a convenient name. Let's call that delta x again, just like we did in the prior example. Now, what's the radius, though, of every disk going to be? Well, that's going to change, right? Okay, the radii are not all the same. But to compute the radius of a disk, what you would do is, much like we did in the prior example, okay, take an x value off of the x-axis that's within that disk, okay? Start there and go up to the edge of the disk. That will be the radius of the disk. Well, what is that radius going to be? So you're going from the x-axis up to what? Up to this curve, correct, right? Okay, what's the formula for that curve? Do you remember? Square root of sine of x, right. So this a height, right, or the radius of this disk is going to be square root of a sine of whatever value you choose here. In other words, in this case, f of x4. All right. So the radius of a disk, right, okay, is f of whatever x value you pick, right? That's the square root of the sine of that that x value. I used let me use an I there for the subscript because you have different subscripts, right? Going from you have different subscripts, right? This I can go to 1, 2, 3, 4, 5, right? But you calculate that radius the same way by plugging that x value into the sine, right, and taking the square root. So there's the radius there of every disk, all right? So what's our estimate for the volume? Well, you take the sum, right, of what? What's the let's see, what's this formula? You have pi, right? And then you have the radius. What's the radius? It's this, right? Square root of sine of these x values, right? And then what do you do with that? Square it. And then multiply by what? Yeah, the width, right? What did I call the width? Delta x, right. How many of these terms are we adding together? From 1 to what? 5, right? Or the number of disks that we pick, right? Okay, which in this example that I drew was 5. All right, so there is the way, if we would do all these calculations, right, that would give us an estimate for the volume. Yeah. Yeah, they are going to cancel out in a minute, so that's going to turn out to be really convenient for us, right? Okay. All right, now look, this is an estimate for the volume. You can get better and better estimates by doing what with the n there? Increasing it, right? So we started with 5, increase it to 100, or increase it to 1,000, but with calculus, we don't have to remain finite, right? Okay. We can really increase that to infinity, but we have to do that with a limit process, right? Oh, by the way, again, when this goes up, what's happening to the radius of each width? It goes down, right? Okay, the radius is getting thinner and thinner. To eventually, you get to kind of just a little slice of bologna, right? Each one of those discs is going to be just really thin, right? Okay, as the number of discs gets really, really large. So what's the exact value for the volume? This is an estimate. What's the exact value? You take the limit, right, as n goes to infinity of this same sum. So remember, that's the pi. That's part of the cylinder formula, right? And then this is the height of every one of your disks, right? Okay, that depends on this function, correct? And then the width of each disk. But how is this limit? What's a better name for this limit? Because see, that's too much to write out, right? Okay. So what's our shorthand for that limit? That's definite integral, right? Okay. That's the definite integral from what to what? 0 to pi of pi times what? Sine of x. Square root of sine of x squared, and then instead of delta x we write what? No, dx, right? Yeah, okay, this is integral. So we write there dx. So this big limit, you can simplify that to this definite integral. Okay, these things mean the same thing. But now, guess what? You have the fundamental theorem of calculus, which says, oh, I know how to calculate this definite integral, right? Let's do that really quickly. So, so I have definite integral from 0 to pi. I can factor out this pi, right? What happens when you square the square root? They cancel, so you just get sine of x dx, right? And I have room down here? Yay, just enough. So what's the antiderivative of sine of x? Be careful, that's not cosine of x, that's sine of x. So what's the antiderivative there? Negative cosine of x, right, okay? It's minus cosine of x. And we're evaluating that from 0 to pi, right? So let's see, I have pi here, and then I have minus cosine of pi minus the cosine of 0, right? Do I remember what these things are? Let's see, what's cosine of pi? What now? It's 1. This would be minus 1, right? Okay. And then, ooh, something is off here, right? What did I do? Yeah, cosine of pi. That's a negative one, isn't it, right? Okay. Oh, so this is plus, right? Okay. Oh, but what's cosine of 0?
But you have a negative.
I did make it positive, right? Oh, but I forgot right here, right? Okay. So this is a plus. Oh, that's better. Yeah. Okay. I thought I was ending up with 0, which we definitely know the volume is not 0, right? But this is minus the minus cosine, right? So that's plus cosine of 0. What's cosine of 0? 1. Oh, so we just end up here with, oh, nice volume there, just 2 pi, okay? So the volume there ends up being a familiar number to us, 2 pi, okay? All right, so so there's an example, right, of definite integration, but now applied to a different problem. All right, let me show you quickly. We have 1 minute. Here is the, here's kind of the summary of what we just did. All right, all summarized into a nice formula for you. So if you have a volume that's created by rotating a region around the x-axis, okay, that is the area beneath a curve around the x-axis, all right, if you have a volume created that way, just like in this football problem, all right, here is how you compute the volume, okay? So this is just repeating what we did, but in general, all right? So the volume is going to be pi times the integral, definite integral from a to b of this function. That is the function that gives you the radius. Usually that's the function that you're rotating around the x-axis, all right, squared, and then dx, that's it, okay? So we can summarize that that big, long definite integration process in this nice, easy formula that we can now use to compute certain types of volumes. What type of volume? It has to be a volume formed by doing what? Yeah, rotating a area beneath a curve around, all the way around the x-axis, okay? So if you have volumes formed that way, this formula can allow you to compute the volume, okay? All right, so we're out of time. All right, so I'll see y'all on Wednesday. We'll look at some more examples like this, but now the examples are very easy because we have this nice formula.